today. So we're still with transients, but closer. First speaker of this session is Richard Anderson, and be careful.
Thank you. Thanks, everybody. My name is Richard Anderson. I'm at EPFL, and it's my distinct pleasure to speak about stellar variability in the era of the Rubin Observatory's LSST. I get asked to give this overview, and I would just like to preface this by a small disclaimer. I only very recently joined the TVS Science Collaboration, and while I do have a bit of a background in stellar variability, I'm not necessarily the person that you would ask to classify all your variable stars. So I feel nervous being in a room full of people who know what the brokers can do, who are very familiar with that survey, as I give you sort of an enthusiast's point of view of what the LSST can do for stellar variability science. And before I go and summarize 202 pages in 20 minutes, I would just like to shout out here the roadmap from TVS that was edited by Kelly Hambleton, Federica Bianco, and Rachel Street. This has been one of my go-to documents recently as I've been preparing, trying to understand really what people have thought of. And there's, of course, a lot of information in here. I encourage you to have a look at that in order to get more detailed ideas of what we can do with stellar variability with Rubin. So in case you're not that interested in stellar variability, I would just like to get one slide of your attention. So some take-home messages here. I think stellar variability is about to enter a new revolution. We will go to the era of hundreds of millions of variable star sources. And this is driven on the one side already by Gaia, but then of course extended very, very significantly by LSST. And this will cover all sorts of types of objects, from very nearby white or brown dwarfs all the way out to extragalactic variable stars. And it's just an absolutely fantastic field to work in. I will try to highlight a little bit the Gaia LSST synergies, because I think this is really wonderful. And just point out here that even among just the galactic variable stars, LSST expects to issue something like 100,000 alerts per night of variable stars. And this is, of course, wonderful for people like me interested in this. And last but not least, since we're here at ESO and talking about the community and how ESO can respond to LSST, it's important to note that the spectroscopic follow-up capabilities at ESO are really insufficient to follow up all this wonderful harvest of variable stars that we will have. And so I do a little bit of self-advertising here for the presentation I will give on Thursday on WST, the Wide Field Spectroscopic Telescope that seeks to do just that. So before we go into any detail of what kind of variable stars, I think it's useful to look a little bit just philosophically how this field has progressed. And I'll start in the 17th century when the first variable stars were identified because people wanted to pinpoint where's the location of specific sources. And Myra actually ended up showing up sometimes, but not other times. And that was how Myra, the Omicron Ceti, was first identified as a variable. Then in the 18th century, more and more dedicated visual searches were conducted to identify what type of variability there is. And for example, John Goodrich identified the delta Cephei variables and also Beta Lyrae eclipsing binaries. And in the 19th century, this was really when photographic plates came around. The big Durchmusterungen, the Bonner Durchmusterung and also the one from the Cape were made to survey the full sky. But that was, of course, still images. And the 20th century CCD cameras in particular managed to add time domain information on select areas of the sky, notably Ogle, Eros, Macho, ZTF came, I guess, in the 21st century. But as we're going further and further into the 21st century, I would posit that what we're really starting to do is all-sky panchromatic video. So there's, from my point of view, no interest in ever going back from this. We will just want to have time-resolved information always, and this is, of course, wonderful for all of us here in this room. Now, Gaia has been up at L2 for about 10 years now, and we just celebrated the 10-year launch event. And Gaia has been really wonderful for stellar variability for many reasons. One, of course, being that it surveys 1.8 billion stars. And in the latest data release, number 3, there were about 10.5 million variable sources in Gaia. That is already the largest variability, just by a small margin, but the largest single variability catalog for stars that was ever published. And in DR4, sort of planned for the end of 2025 or so, this will be increased by an order of magnitude. So already Gaia will deliver 100 million variable stars with chromatic variability due to the BP and RP spectrometers, spectrophotometers, and the G-band photometry, plus, of course, all the wonderful astrometry that you have, proper motions, parallaxes, and so on, that will even allow to measure the astrometric motion of binary systems. But LSST will go much further. It has 6 bands instead of just 3. It goes about 4 magnitudes deeper. Here are some numbers from Federica's paper. And for example, in the Deep Wide Fast survey over 10 years, the distribution of visits in the different filters is given here. This compares quite well to the mean number of observations that Gaia does also in 10 years. So I just point that out here because we're really dealing with sort of not too dissimilar numbers, apart from the fact that LSST, of course, goes much fainter. Then in the deep drilling fields, there will be about 20,000 observations, meaning many, many more per night. And this is, of course, fantastic for all sorts of short timescale variations. And so these 2 deep wide and deep drilling field surveys are supported by mini surveys that would target specific regions, such as the Magellanic Clouds, for example, or the Galactic Bulge. And then there was also a proposal by a proposal to target one specific field for a full long winter night in order to see all sorts of stellar timescales in that domain. So LSST, unfortunately, only starts just as Gaia is winding down. So there's probably no overlap in time specifically. That's a bit unfortunate. But in terms of precision as a function of magnitude, it's just perfect. If you look here at this plot showing the mean uncertainty in the Gaia G-band as a function of G-band magnitude, you see this kind of curve here. It's important to realize that Gaia is, of course, a magnitude-limited survey, just like LSST. And so you see here M31 by the source counts in Gaia. Of course, LSST will do this to much, much greater distances. And not just that, in this faint range of Gaia, you see here the 5 millimag error floor that LSST has at the bright end, right? So if we look at this, it means that we get 5 millimag precision per epoch, all the way from 6 to 23rd or so magnitude. This is absolutely fantastic for stellar variability of all sorts. And of course, we get this in many different filters. Now, why are we really that interested in stellar variability? Well, we're passive observers in astronomy, and variability is the closest that we get to perturbing our sources. The sources are oscillating or doing something funny, and we can see how they react to that perturbation. And that's, of course, immensely useful for stellar physics, but also a host of other applications, including the distance ladder that I'm particularly interested in, or even the atmospheres of brown dwarfs, supernova explosions, and so on. And there's a huge diversity of stellar variability. This is a kind of now emblematic diagram called the Variability Tree, that splits up variability in 2 types of categories: the extrinsic variability types that more depend on your view of the variability that you're analyzing, versus the intrinsic variability that is due to the source's behavior itself, that is intrinsic to that source. And this splits up into many different categories. Among the stars here in extrinsic variability, you have microlensing, you have eclipsing variables, and you have rotation, because that's sort of seen as a point of how you see the source. And then under the intrinsic ones, you have a different type of eclipsing variables. You have eruptive variables, and we will hear Anna Pala speak just later today about white dwarfs and cataclysmic variables. And you also have a huge variety of different types of pulsating stars, and Giulia De Somma will be talking specifically about the radial pulsating stars like the delta Cepheids. And of course, you also have secular variability, where you really see the source evolving on human timescales. And of course, LSST would cover all sorts of these things. And to give you an idea of the relative distribution of these types of sources, we can look at what Gaia DR3 actually assigns in terms of classifiers. So of the 10.5 million, 10% turn out to be AGN. Okay, these are not stars, but we have about 34% pulsating stars, 28% rotating, 22% eclipsing, and all the rest is 6%. Now, a very important point is that stellar variability, the kind that you can detect, depends on the population that you study. It's very different from supernovae that are more isotropically distributed over the sky. If you look at certain types of variability, they will trace different populations. And in particular, an eclipsing binary is mostly a question of chance alignment and matching source radii and so on, and the orbital periods of whether or not you see a source in transit. So the eclipsing binaries here, 2.2 million from Gaia to year 3, they essentially trace just the distribution of stars within that magnitude limit. Eclipsing binaries, of course, would show various types of light curve shapes, and there's a very good study by Andrzej Presza from 2011 that describes this in detail. They expect about 24 million eclipsing binaries in LSST. That is a factor of 10 more that we currently have in Gaia, and of course will contain a lot of very interesting objects for further study, because you see, for example, the ratio of the radii due to the transit depths of the sources. Out of the 24 million, about 6.5 or 6.7 would be fully characterizable by the photometric pipeline, and about 1.7 million would be double line spectroscopic binaries. Now, those are particularly important because you can measure really the total, the masses of the systems as well as the radii. And for example, you can measure distances using these types of systems. Now, there should also be about 1 million contact binaries where you see variations due to the deformation of the star that is in contact. And there could even be one or two events where you see the coalescence of the contact binary in real time. And so while you, of course, will see huge numbers of certain groups that you're quite familiar with, it's also the finding that gem hidden in the data that will be quite tricky. And I will leave it up to the experts on the alerts to tell me how you can actually dig that out early on in the survey in order to be able to define your follow-up strategy that would give you the most informative data for a one-off event in something like LSST. Then, of course, if we go to even shorter periods, there's the ultra-compact binaries, let's say periods of order 10 minutes or so. Those would be preferentially very faint and found in the deep drilling fields. And those could even serve as continuous gravitational wave calibration sources for things like LISA. So this is also very, very interesting. My own personal hopes for eclipsing binaries is that we would get lots and lots of eclipsing binary systems that contain pulsating stars, because then we can really have Rosetta Stone type systems that will tell us more about the pulsations and about the structure of these stars, as well as objects at extragalactic distances, so the local group or beyond even, where we can measure geometric distances from the late type eclipsing binary, detached eclipsing binary systems, similar to what the Araucaria team has done in the LMC. And then finally, multiplicity is of course not at all limited to only the sources that are eclipsing. You can measure multiplicity using astrometry, and for example, proper motion measurements combined from Gaia and LSST will be even better in terms of this method. You can measure them chronometrically. In particular, if you have a pulsating source, you can measure modulations in the pulsation as stars are orbiting. You can measure microlensing, ellipsoidal variations, and so on. And of course, binaries are not the only form of multiplicity that exists. Here you see an example of a sextuply eclipsing sextuple system. This has been measured in TESS. These kind of complications, of course, can also arise and are particularly interesting. Now, I mentioned microlensing, and this is the only slide I have. Sorry, Rachel. But basically, microlensing is, of course, the distortion of space-time as you have a foreground lens that leads to an increase in magnitude that is time-dependent. And of course, LSST will pick this up in large numbers, and so this will constrain all sorts of very interesting phenomena, be it free-floating planets or potentially massive compact halo objects and so on. It's a big field. Please look at the TVS documentation. But it doesn't have to be a single source. You can also have binary sources, and here's a really beautiful example from Gaia that was one of the early images of the week from Gaia. Now, coming a little bit closer to my own personal favorite of type of variability is on pulsations. They're immensely useful for many applications. The one thing that I want you to really take home, if you're not at all familiar with this, is that pulsation cannot occur everywhere in the Hertzsprung-Russell diagram. Pulsation is always intricately related to the structure of the star, and so different regions in the Hertzsprung-Russell diagram will feature specific type of pulsations. And in particular, there's kind of a relation here acoustic oscillations that mean that down here you have periods of order of minutes, and up here you have periods of order years. And so with LSST, you're actually covering that whole range, because with your 30-second exposure split in two, you're going down to the white dwarf regime, while your 10-year survey will really probe the long period evolved supergiant stars like Miras and whatnot. And here's an example of what this looks like in Gaia. You actually can show very nicely these loops. The color information for pulsating stars is extremely powerful for your classification. So for all of those interested in classifying variables, make sure to account for the chromatic variability of pulsating stars. This is a good first step to try and disentangle eclipsing systems, for example, from pulsating systems. Pulsators usually change their temperature. And as I mentioned, different types of variables probe different parts on the sky. Here you see the sky distribution of 270,000 RL-Lyrae stars from Gaia, where you can, for example, see very nicely the dwarf Sagittarius galaxy here merging with the Milky Way. This is just the sky distribution of the RL-Lyrae stars. So it's an old population and, of course, looks very different from the eclipsing binaries. However, pulsating stars frequently also allow you to understand metallicity. Earlier, there was I think one of the lightning talks that mentioned a light curve relation with metallicity. Here you see the overall sky map of something like 170,000 or so RL-Lyrae stars and the metallicity inferred from the light curves. So you can use that variability to infer properties of your host population, for example. And last but not least, of course, pulsating stars are standard candles, and this is what I'm really interested in, so please come talk to me if you're interested in that subject, of course. Thanks to Henriette Leavitt's work from about 120 years ago, or 15 years ago, we know that the brightness of these sources correlates, here classical Cepheids, correlates very well with the log of the period. And because the variability is very straightforward to recognize in other galaxies, it allows you to understand the absolute magnitude of the source once you've calibrated these Leavitt laws. And because flux diminishes as distance squared, you can use them to measure luminosity distances. Now, the Ogle survey in particular has been fundamental for determining these kind of relationships. And here's just a beautiful PL relation from Ogle 4 of the LMC with 4,620 classical Cepheids. These stars, of course, calibrate the first rungs of the distance ladder shown here. This is a plot from the Shoes collaboration from Adam Rees et al., where essentially to measure the Hubble constant, you build a distance ladder that involves pulsating stars on the first two rungs and then supernovae on the last two rungs, and you cross-calibrate them here in the middle. Basically, you need to know pulsating stars with known geometric distances to calibrate the supernovae that will then help you measure the Hubble flow. The point of what I want to bring here is that LSST will actually measure supergiants out to about 30 megaparsecs, Miras out to 15 megaparsecs, Cepheids to 10, RGB stars to 6 megaparsecs. All of this is significantly beyond the local group, and so you could maybe think of LSST as Ogle, but within a way, way larger volume, being able to understand where all of these sources are. You only need to detect them. You don't necessarily need to measure the mean fluxes. Those you can measure with other facilities like ESO, like HST, James Webb, and so on. But this will take an inventory of these crucial standard candles that's just going to be fantastic. Right, and then, sorry about the formatting, there's other mini surveys that have been proposed that are also very, very informative of this. So there will be an unprecedented ability to study stellar standard candles in this era. Now let me get to a couple of musings and conclusions of all of this, because I wanted to give an opportunity for food for thought, essentially. LSST, of course, with its sampling will be initially very good for very short periods, and then maybe also for longer periods. The in-between timescales, if I understood the TVS document correctly, will be more studied once there are years or longer timescale data available. There will be many, many alerts issuing on variable stars every night. And as I mentioned, the synergies with Gaia will be really fantastic. So we'll need ancillary and follow-up data for many of these. And that brings me to a very interesting question that I find. I don't know, maybe it's been answered, but it's the question of which of the sources should be really followed up. And there's one element I'd like to put on the table, which is that urgent is not equal to important, as everybody who's looked at the Eisenhower diagram knows. Important, right, is something you define by the scientific impact. Urgent is something that has to do with time criticality and whether you need to assign a TOO mode or something like this. We will be swamped with alerts of TOO systems, and we must make sure that even persistent variable sources are followed up adequately. And so I think there will be some difficult trade-offs here in terms of number of sources, cadence, depth, area, and so on. But I think it's useful to think of this from the point of view of how ESO wants to approach this. And then I think Bruno may have mentioned it earlier, having kind of a multi-mission archive as a baseline for alerts, if it's not already implemented, apologies for my ignorance there, could be quite useful. So just to conclude, LSST will be a major catalyst for the more than 100 million variable star revolution. That classification task is major and will evolve AI, but mind you also that the variability that LSST will pick up will vastly exceed our training sets. We're going way fainter than what we've done previously, and hopefully, right, we're all hoping for this, there will be new things that are not part of that training set, and so of course we need to keep an eye out for that. Spectroscopic characterization is crucial for many of these types of variables I showed you earlier, whether you see radial velocity variability or specific line shapes. And in terms of how ESO will address this, I think the ELT will, of course, be absolutely fantastic going faint and deep for maximum priorities objects. Similar for the VLT, where you do have some multiplexed instruments, but of course the field of view is small. And foremost, it's just a small telescope compared to LSST. So of course it's a major leap ahead. It's super exciting, but it's not really a match to what LSST will do. And so I do think that spectroscopy will be the bottleneck for this. And again, please come check out my presentation on Thursday.